So dear students, again we are back to our online discussion on NMR spectroscopy. In the previous class we were going through the concept of the nuclear magnetic dipole moment. Okay, we found that the spinning nuclei are having the angular momentum and also they have magnetic dipole moment. And the angular momentum of the spinning nucleus depends upon the spin of the nucleus. If the spin of the nucleus is s, then the angular momentum I is equal to root of s into s plus 1 into h divided by 2 pi. And then we counted this h divided by 2 pi as 1 unit. Then angular momentum I is equal to root of s into s plus 1 unit. Okay. We learned this in the previous class. Then we also learned that the spinning nuclei will have a magnetic dipole moment associated with them, right? And this dipole moment of the spinning nucleus or magnetic moment of the spinning nucleus, dipole moment means magnetic dipole moment, okay? Or magnetic dipole moment or magnetic moment of the spinning nucleus mu is equal to G beta n into root of s into s plus 1 joules per Tesla. Okay, that is the magnetic moment mu, and this is what we learned in the last class. Here G is the nuclear G factor, which has a unique value for each nucleus, and beta n is the nuclear magneton, and the value of nuclear magneton is 5.05 beta n 5.05 into 10 raised to minus 27 joules per Tesla. That also we learnt in the previous class. And G in the case of H11, G is equal to 5.585. These are the things we were discussing in the previous class. Today we are going to learn what will happen to this spinning nucleus if that spinning nucleus is kept in an external magnetic field. Okay, obviously you know that associated with the spinning nucleus there will be a magnetic moment, because the spinning nucleus can be considered as a tiny bar magnet, and when this tiny bar magnet is inside a very big magnet or an external field, then this tiny bar magnet will interact with the external magnet. Okay, and we are going to learn about this interaction today. And before proceeding, you have to go through a quantum mechanical rule or quantum mechanical consequence of the angular momentum of the nucleus. You might be already knowing this because you have already learned this in your previous classes, I mean the BSc classes, but once again we will go through that. Okay, you know that the spinning nucleus has an angular momentum, the expression for which has been already written here, that is I is equal to root of s into s plus 1 unit. And if we are considering the orientation of this angular momentum, why I am talking about orientation? Because angular momentum has a direction and it has a magnitude as well. Therefore, angular momentum can be considered as a vector. Okay, so this vector will have an orientation, but there are some quantum mechanical restriction about the orientation of this angular momentum vector. What is that restriction? And the quantum mechanical restriction comes in such a way that it will not allow all the arbitrary direction for the angular momentum. With respect to a reference direction, only certain restricted directions are allowed for the angular momentum vector of the nucleus. Okay, we are considering a reference direction. Let this reference direction be the z-axis. Actually, this reference direction is marked by an external magnetic field. Means you have to suppose that in the Z direction, the external magnetic field is being applied, or the lines of force of the external magnetic field is in the Z direction. Okay, lines of force of the external magnetic field is in the Z direction. That is how we have set the reference direction. And when the nucleus is placed in this external magnetic field, with respect to this reference direction, its angular momentum will take some particular orientation, or the angular momentum will take some selected orientation or restricted orientation. Okay. Suppose that you have a nucleus, the nucleus is H12 here, H12. And what is the spin of H12? We learned that already in the previous class. The spin of this nucleus is equal to 1. Spin is equal to 1, or S is equal to 1. Therefore, angular momentum of this nucleus, I is equal to root of 1 into 1 plus 1 of root of 1 into 2, that is equal to root 2 units. Okay, root 2 units, where 1 unit is h divided by 2 pi. Okay, that is the angular momentum of this nucleus, and root 2 unit is equal to 1.41 units. 1.41 units. Means if you are considering the H12 nucleus or the nucleus of deuterium, then you can see that the angular momentum of this nucleus is 1.41 units. This has an angular momentum because it has a spin also. The spin is an integer quantity, that it is 1. Okay. And in this case, the quantum mechanics says that if the spin is an integral number, like 1, 2, 3, etc., if spin is an integer, then this angular momentum can orient in space only in certain restricted direction, such a way that the component of the angular momentum in the reference direction should be integral units. Did you understand anything? Okay, I will explain. Okay, we have the spin as an integer number. Spin is equal to 1 here in this case. And the angular momentum is 1.41 units. And I am going to draw the angular momentum vectors with respect to this reference direction. And I am going to draw so many angular momentum vectors in so many arbitrary directions. Okay, but all the angular momentum will have 1.41 units as the magnitude. So how many angular momentum vectors in many arbitrary directions I can draw? I can draw infinite number of angular momentum directions, right? If I am taking a semicircle like this, a semicircle, and this semicircle has the center here, and the radius of this semicircle is 1.41 units. The radius of the semicircle is 1.41 units. Means the distance from here to here is 1.41 units. That is actually a root of s into s plus 1, right? That is what is 1.41 in this case. That is 1.41 unit. Since it is a vector, I am drawing it like this with an arrow in the head. Okay, and so this represents an angular momentum vector. I can draw many angular momentum vectors of the same magnitude. Why not this one? This is an angular momentum vector of the same magnitude. Why not this one? This is also an angular momentum vector of the same magnitude. This one also an angular momentum vector of the same magnitude. Let me draw it here, and let me draw it here. Let me draw it here. I can continue this until the evening, no problem. I can draw many directions here. Okay, and all these are the arbitrary directions, the directions which I have chosen. But here there is a problem that the quantum mechanics plays a restriction there. The restriction is that since the spin is an integer number, okay, since it has an integral spin, then quantum mechanics says that you have to look into the component of the angular momentum in the reference direction. Okay, we have to look into the component of the angular momentum in the reference direction. Let us look into the component of the angular momentum in the reference direction. After that, I will tell what else the quantum mechanics is saying. So first, let us look at the component of this angular momentum in the reference direction. And let me take the component of this one, this vector, okay, this vector. How can I take the component of this vector? Let me just draw a perpendicular to the reference direction. So when I am drawing a perpendicular to the reference direction, it meets here in the reference direction. In this point it meets, okay. So the component of this angular momentum in the reference direction is this one. See, this is the component from the center to the point where the perpendicular meets. That is the magnitude of the component. So the component is this one, okay. And what is the value of this component? Okay, when I am checking the value of this component, this is something like 1.3. Okay, magnitude of that component is 1.3 because this is 0 and here where the circle meets it is 1.41 units. Okay, circle meets at 1.4 units because the radius of the circle is 1.4 units and the point is just below that. So let me assume that is 1.3. So the magnitude of the component of the angular momentum for this particular direction is 1.3 units. And when I am taking the component of the second one, then that is when I am drawing the perpendicular meets here, okay, and the value of that is 1.0 or 1, okay, that meets at 1, okay. So the angular momentum component in the reference direction corresponding to this second direction is this one from 0 to this, okay, this is the second angular momentum component. And I can draw the perpendicular again from the third one, then I get it here, that is 0.5. So the component has the magnitude 0.5. This is the third one. The component has 0.5. So I can again do this with this one. So the component of this one, and I am again drawing the perpendicular from the head of this vector, then it meets at 0, okay. It means that the component is here itself, that is the value, the magnitude of the component is 0, okay. Then one is this one and the magnitude of this one is 0.5, but here it is in the reverse direction, therefore I can say that is minus 0.5. It meets at minus 0.5. If you are considering this as the z-axis, this is 0 and whatever value you are taken above that, there will be positive values. The values that you are taking below will be the negative value. Therefore, the component or the perpendicular meets at 0.5, okay. And here it meets at minus 1.0. and this meets at minus 1.3, okay. So the component of this one is from here to here. This is, see, here is a component from 0 to 0.5. In the opposite direction of that there is another component. They have the same magnitude. This one and this one have the same magnitude, but they have different direction. Like that, there is a component from 0 to 1.0. In the reverse direction also there is a component from 0 to minus 1.0. So they have the same magnitude but have different direction. There is a component from 0 to 1.3 and here also there is a component from 0 to minus 1.3. So it has same magnitude but different directions. So I have taken so many arbitrary directions here, and with respect to these arbitrary directions I have taken the components in the z-axis. And when I am taking the components in the z-axis, I get the components of different magnitudes. That is, here in this case the components has a magnitude of 0, 0.5, 1.0, 1.3. Here also in the reverse direction we have the components with the magnitude 0.5, 1.0, 1.3 in the reverse direction. Okay. So I have many components. Now again we are looking into quantum mechanics. Okay. So we are waiting to see what quantum mechanics says next. Quantum mechanics asked us to take the component in the z-axis. We took it and we evaluated the components corresponding to different angular momentum directions in arbitrary directions. Okay. Now we have to listen what quantum mechanics says second. Now quantum mechanics says that you pick only those directions for which the component is an integral value, or the component in the reference direction should be integral units including 0. Okay. So we have to pick only those angular momentum directions for which the component is an integral unit. We can check which of the angular momentum directions will have the component as the integral unit. Okay, let us take the first one, and this angular momentum from here to here. This angular momentum has a component 1.3, that is not an integral unit. Therefore, this is not quantum mechanically allowed. Now let us examine the next one from here to here, and it has a component of 1.0. Therefore, it is quantum mechanically allowed. Okay. And let us check the next one, this component, and it has this angular momentum. It has a component of 0.5, that is not an integral unit. Therefore, this is not quantum mechanically allowed. So let us check the next one from here to here. This vector has a component 0, so that is allowed. Okay, that is allowed. And this one, it has a component minus 0.5. Means in the reverse direction there is a component having the magnitude 0.5, that is not integral unit, that is not allowed. If we are checking this one, its component has a magnitude which is an integral unit, so this is allowed, and this is again not allowed. Okay. So out of these arbitrary directions, only 3 are allowed. 1, 2, 3. 3 are allowed. Other directions are not allowed. You can draw n number of other directions, all the arbitrary directions, but you can draw it from morning to evening. But quantum mechanics says no, you can draw it, but it is not allowed quantum mechanically. If it is a nucleus having if it is a nucleus having an integral spin, only those components are allowed whose magnitude are integral units. So this is a quantum mechanical restriction. What would we say? There is a quantum mechanical restriction on the spatial orientation of the angular momentum of the nucleus. The quantum mechanical restriction is that the angular momentum vector of the nucleus can only orient in certain restricted directions, for which the components in a reference directions are all integral units if the spin is also an integer. Okay, or if the spin is integral, then the component in the reference direction should be integral units. So that is a quantum mechanical restriction. So there is a quantum mechanical restriction on the orientation of angular momentum, and we now consider a case for the spin is an integer. Okay, so we can call the component of the angular momentum in the reference direction. For example, here this is z direction as iz. Okay, in this particular case, which are the iz values? Okay, one is corresponding to this one. Okay, I am making it bold. The allowed directions are in bold. This is also an allowed direction, and this is another allowed direction. Okay, these are all bold. Okay, these are the only allowed directions, and in these corresponding to the first allowed direction, the component is 1.0. Therefore, Iz is equal to 1. Okay, And corresponding to the second allowed direction, the component is 0, therefore Iz is equal to 0. And corresponding to the third allowed direction, the component is minus 1. Iz is equal to minus 1. Okay. So these are the components of the angular momentum in the reference direction. All other angular momentums are ruled out. Okay. So here we can come to a generalization. Here you can see that in this particular case S is equal to 1 or spin is equal to 1. That is why Z values are 1, 0, minus 1. If so, if spin is equal to S, spin is considered as S, then which are the Iz values possible? Iz values possible are yes, then one number less than S, that is S minus 1, etc. to 0, etc. to then negative of whatever are in this side, then the negative quantities of the same in the other side, that is minus of S minus 1, minus of S minus 1, then minus S. Okay, these are the components. Then how many components will be there? In this direction, S components. That is in the left side of the 0, there will be S components. The other side of the 0, that is right side of the 0, there will be S components, and the left side also there will be S components. Then including 0, 2 into S plus 1. അല്ലേ, ഇങ്ങോട്ട് എസ് കമ്പോണൻസ്, അങ്ങോട്ട് എസ് കമ്പോണൻസ്, പിന്നെ സീറോയും കൂടെ കൂട്ടി എസ് പ്ലസ് 1. That is totally there will be 2s plus 1 components. Okay, so 2s plus 1 Iz values will be there. Okay, this is a case when S is an integral value. Okay, now we can check what is the case when S is a half integral. For example, we can choose the case of H11. We can choose the case of H11. Let me draw it here. Let us choose the case of H11. Then in this case spin S is equal to half. Therefore angular momentum I is equal to root of S into S plus 1, that is root of half into half plus 1 units. Okay, that is equal to root of half into 3 by 2, that is root 3 divided by 2. Okay, root 3 divided by 2. Root 3 divided by 2, that is equal to 0.86 units. 0.86 units. Therefore, the angular momentum of H11 nucleus having the spin half is equal to 0.86 units. And now we are going to consider all the arbitrary directions of this angular momentum with respect to the reference direction. And again, our reference direction is Z direction. This is a reference direction, Z direction, okay, Z axis. And this is the origin, that is the point where 0 is. And I am going to consider so many directions for the angular momentum. And for that, I can again draw a semicircle. And this semicircle has a radius of 0.86, means this value is 0.86 units. Okay, and this is a root of S into S plus 1 in this particular case, 0.86 units. And how many arbitrary directions I can choose here? Many. Why not? I have the time, so I can draw so many arbitrary directions. Anyway, since I want to conclude this class within a certain time, I am not going to draw so many directions. I will restrict within 3 or 4 or 5 directions. Okay, so let me draw this one. And then let me draw this one. Okay, or I can draw it perfectly, more perfection. Okay, then I can draw this one, then I can draw this one. This is already there. Okay, this one is already there. Okay, then I have drawn 1, 2, 3, 4, 5. 5 arbitrary directions. And all these angular momentum have the same magnitude, but they have different directions. Okay, and now I am checking what is the component for each of these arbitrary directions. Let me check the component of the first one and this one. And I am going to draw a perpendicular from here to here, and this is a circle of radius 0.86. So this is something like a 0.7. Okay, 0.7 units. And now I am going to check the component of the next one. The component of the next one, it will be like this. This one will be the component of the next one from 0 to here. This is the component of the next one, and it has a magnitude 0.5. Okay, and then I am checking the component of this one. When I am drawing the perpendicular from the head of this arrow, then that meets at 0, means the component is 0 itself. Okay, there is another component that is at 0. That means that it has no magnitude. And then this one. Okay, and it's a magnitude. So this is the component from 0 to here in the reverse direction, that is minus 0.5. To here it is minus 0.5, and from here to here it is minus 0.7. Okay, so different components I have drawn there. Different components are there. The components are like this. See, the component is also a vector, and this is in the z direction. All the components are in the z direction, and its magnitude should be measured from the origin, means from 0 to here. And the first component is 0 to here, that is the magnitude is 0.7. Second component is from 0 to here, magnitude is 0.5. The third component is like this, and the third component is 0 itself, and the next one possible is from 0 to minus 0.5. That is, this has the same magnitude of this component. Okay, but it has opposite directions, and again there is a component from here to 0.5. Okay, so these are the components. All the components are of the angular momentum are in the z direction, but they have different magnitudes. So we have the magnitudes like 0.7, 0.5, 0.0. Then again the reverse direction, we have the components which have the magnitude 0.5 and 0.7. Now quantum mechanics says that wait, there are some restrictions. In this case, the spin is a half integer value, right? The half integer value means in this case the spin is 1 divided by 2, that is a half integral value. So if you are seeing half integral values for the spin like 1 by 2, 3 by 2, 5 by 2, etc. If you have half integral spin for such nuclei, the angular momentum can orient only in those directions for which the component of those angular momentum in the reference direction should be half integral units. Component in the reference direction should be half integral units. So we can check which are the half integral units as the component here. The first orientation, this one from here to here, the first orientation, its component is 0.7, that is not a half integral unit, so this possibility is ruled out. The second orientation, that is from here to here, this is from here to here, okay, and its component is 0.5, has the magnitude of 0.5, so that is allowed. And the next one is this one, its component is 0, that is not a half integral unit, therefore this is not allowed. And next one, this one, its component is 0 minus 0.5, right? So its magnitude is 0.5, so that is allowed. And the next component is minus 0.7, it is not half integral unit, so that is not allowed. So which are the angular momentums allowed? Which angular momentum are allowed in this case? Only two angular momentum are allowed. One is this one is allowed, whose component is 0.5. And another angular momentum is this one, whose component is minus 0.5. Only two angular momentum directions are allowed here, quantum mechanically allowed here. There is again a spatial restriction. So, in the case where the spin is a half integral value, in those cases the angular momentum can orient in space only in certain restricted directions, so that the component in the reference direction should be half integral units. Half integral units. Okay. So, in this case, that is the rule. Therefore, in this particular case, S is equal to half. Therefore, Iz in this particular case is equal to plus half and minus half. Plus half and minus half. These are the Iz values. One Iz value is plus half and another Iz value is minus half. So, in general, if the spin is S, the half integral spin is S, half integral spin. If the half integral spin is equal to S, then in that case, the allowed Iz values are minus S, then S minus 1, etc. to half, okay, then minus half, etc. to minus of S minus 1 to minus S. Okay, these are the allowed components. Okay, so S2 minus X through minus half, through half and minus half. Okay, these are the components possible here. Therefore, in this case, for example, if S is equal to 5 by 2, if S is equal to 5 by 2, and in those case Iz is equal to, which are the possible Iz values? So, we have according to this, the first Iz value is S itself. So, it is 5 by 2. Then S minus 1, that is equal to 3 by 2. Then after that half, okay. Then minus half, then minus 3 by 2, then minus 5 by 2. These are the possible components if S is equal to 5 by 2. Okay. I hope now you understood. So, how many values are possible? In this case, when it is 1 divided by 2, only 2 values are possible. When the spin is equal to 1 divided by 2, 2 Iz values are possible. So, what is the relation between half and 2? Half and 2. 2 is equal to 2 into half plus 1, right? I can write like that. 2 is equal to 2 into half plus 1. So, when S is equal to 5 by 2, how many components are there? 1, 2, 3, 4, 5, 6. 6 components are there. What is the relation between 5 by 2 and 6? That is, 6 is equal to 2 into 5 by 2 plus 1. 2 into 5 by 2 plus 1. So, if spin is equal to S from this one, if spin is equal to S, then how many components are possible? 2 into S plus 1, 2 into S plus 1, here also 2 into S plus 1. So, 2S plus 1 components are allowed. If spin is equal to half, then 2 components are allowed. If spin is equal to 5 by 2, 6 components are allowed. So, that if spin is equal to S, 2S plus 1 components are allowed. Okay. So, this is the quantum mechanical restriction for the spatial orientation of the angular momentum. So, let us conclude once again. The nucleus, the spinning nucleus has an angular momentum, But this angular momentum cannot orient or point in all the arbitrary directions. The angular momentum can point only in certain directions, for which the component in the reference direction should be all integral values if the spin is an integer, or all the components should be half integral units if the spin is a half integer. That is the quantum mechanical restriction for the orientation of the angular momentum. Okay. Now you know this. There are some restriction for the orientation of the angular momentum. After this, now we can proceed. Now, I said that the reference direction is marked by an external magnetic field. So, in an external magnetic field, the nuclear spin cannot take any direction for the angular momentum, right? And that depends upon the direction of the external field. With respect to direction of the external field, only the nuclear spins can orient. Okay, that is what we said. Now, let us closely examine these cases. So, we already know that the magnetic moment mu is equal to G beta n into root of S into S plus 1 joules per Tesla. Okay, this we already know. That is a magnetic moment. Now, what about the component of the magnetic moment in the reference direction? Here the reference direction is Z direction. So, what about the component of the magnetic moment in the reference direction? The component of the magnetic moment in the reference direction mu is equal to G beta n into the component of this quantity in the reference direction. What is the component of root of S into S plus 1 in the reference direction? See, this is root of S into S plus 1. This is also root of S into S plus 1. The component of this root of S into S plus 1 in the reference direction is nothing but IZ. This case is IZ എന്ന് പറയുന്നത് ഏതൊക്കെയായിരുന്നു 1 0 minus 1. ആ കേസിലാണെന്നുണ്ടെങ്കിൽ IZ എന്ന് പറയുന്നത് പ്ലസ് ഹാഫ് മൈനസ് ഹാഫ് ഇതായിരുന്നു അല്ലേ. അപ്പോൾ component of the root of S into S plus 1 in the Z direction, that is IZ. Therefore, the component of the magnetic momentum in the S direction is equal to G beta n into IZ joules per Tesla. That is the component of the magnetic moment in the Z direction. Then we can now think certain things. I already said that for most of the nucleus, the G value is a positive value for most of the nucleus, but that's not the case always. Okay, in certain nucleus G value is negative as well, but in most of the nucleus G value is positive. We are particularly interested in the hydrogen and carbon. For both of these the G value is positive. Okay, therefore we will particularly looking into hydrogen in 80% of the case. When we are studying this, we will be looking into hydrogen. So especially we are interested in the G value of the hydrogen, and that is 5.585, and that's a positive quantity. So let us conclude that G is positive for most of the nucleus, especially for the nucleus of our interest. And beta n is also a positive quantity. You know this, beta n is equal to nuclear magneton, that is a positive quantity. So since G and beta n are positive, then the mu Z will depend upon the sign of IZ. IZ can be either positive or negative, right? It can be positive or negative. So, whatever may be the sign of the Iz, that same sign will be transferred to mu Z, because G and beta n are positive quantities. If G or beta n were negative quantities, it would be reversed, right? For example, if G is negative, as in the case of certain rare nucleuses, rare cases of the nucleuses, G is negative. So, in that case, then the Iz and mu Z will have opposite side, right? But in our case, in most of the cases, then G is positive. Therefore, Iz and mu Z will have the same sign, either positive or negative. Or we can say that whatever may be the direction of the angular momentum, the magnetic moment also will have the same direction. Or whatever may be the direction of Iz, the same will be the direction of mu Z. Iz ന്റെ അതേ ഡയറക്ഷൻ ആയിരിക്കും mu Z നും ഉള്ളത്, അല്ലേ? അപ്പോൾ ഈ കേസിലാണെന്നുണ്ടെങ്കിൽ Iz, either the Iz can be from bottom to top, okay, ഇങ്ങനെയുള്ള ഡയറക്ഷൻ ആയിരിക്കും. Otherwise the Iz can be from top to bottom. അപ്പോൾ രണ്ട് ഡയറക്ഷൻസ് ആണ് Iz നുള്ളത്. ഒന്നുകിൽ Iz ഇങ്ങനെയായിരിക്കും, അല്ലെങ്കിൽ Iz ഇങ്ങനെയായിരിക്കും, അല്ലേ? So, this is Iz is equal to half, and here Iz is equal to minus half. Okay, these two possibilities are there. So, Iz and mu Z will have same direction. Therefore, the mu Z corresponding to this Iz, will also have the same direction. Okay, and mu Z corresponding to this Iz is equal to minus will also have the same direction. അപ്പോൾ mu Z നും Iz നും ഒരേ ഡയറക്ഷൻ ആയിരിക്കും, സെയിം ഡയറക്ഷൻ. That is what we have to understand from this equation. Mu Z and Iz have the same direction. This has a serious consequence. We will understand that shortly. Now, let us consider that the nucleus is placed in the external field, okay, and the external field has the direction of Z. And in order to explain this, I am going to explain this in more detail in order to understand this, because otherwise it would be confusing for most of the students. Okay. Let us consider that we are creating a magnetic field using a horseshoe magnet, like this. We are creating the magnetic field using a horseshoe magnet, and here is the north pole, okay, and here is the south pole of the horseshoe magnet. If you want, you can put it in the reverse direction. Also, it depends on you how you place the horseshoe magnet. No problem. I am placing it like this. And obviously, since this is a magnet, it has magnetic lines of force. What's the direction of the magnetic lines of force? Conventionally, we are choosing the direction of the magnetic lines of force in such a way that inside the magnet, the lines of force will be from south to north. Okay? മാഗ്നറ്റിന് അകത്തൂടെയാണ് നമ്മൾ മാഗ്നറ്റിക് ലൈൻസ് ഓഫ് ഫോഴ്സ് പരിഗണിക്കുന്നതെന്നുണ്ടെങ്കിൽ സൗത്തിൽ നിന്ന് നോർത്തിലേക്കാണ് ലൈൻസ് ഓഫ് ഫോഴ്സിൻ്റെ ഡയറക്ഷൻ. സോ യു ക്യാൻ ഡ്രോ ദ ലൈൻസ് ഓഫ് ഫോഴ്സ് ഇൻ ദിസ് ഡയറക്ഷൻ from south to north, like this, south to north. So the magnetic lines of force will have this direction from south to north. And what happened when these magnetic lines of force emerge out of the magnet? The magnetic lines of force should emerge out of the magnet, so that the magnetic lines of force should be extended from here to here, right? And what will be the direction then? See, it is from south to north, then it is coming in this direction. When it is emerges, then it will be like this. So if you are considering the magnetic lines of force inside the magnet, it is from north to south, right? Or if you are considering a bar magnet like this, And if you are considering this is south and this is north, and the magnetic force of lines inside the magnet will be from south to north like this, then it emerges the magnetic magnet, then it will proceed like this, say like this. So this will proceed like this from if you are considering the magnetic lines of force outside the magnet, it is from north to south, right? But inside the magnet it is from south to north, like that. So you are considering a horseshoe magnet like this, okay? And we are going to place our nucleus here between the south pole and north pole of the horseshoe magnet. And here you can see that it is the magnetic lines of force near the nucleus is from north to south. I am going to enlarge this picture so that you can understand it better. Let me rub it off, all these things, okay? So we are considering the horseshoe magnet. I am not going to draw the full magnet here because it's already enlarged, but you know this. This was the south pole of the horseshoe magnet, then it comes like this, and here comes the north pole. North pole comes here. And the magnetic lines of force were like this inside the magnet from here to here, and then it comes here, emerges out of the magnet, and then from north to south it will proceed like this. Okay, from north to south like this. So this is the direction of the magnetic force of lines of force, and this is where we are going to place the nucleus. We are going to place the nucleus inside this magnetic field. So when we are placing the nucleus inside this magnetic field, as you know, the nucleus can have only certain restricted orientation, right? Certain restricted orientation. If you are considering the hydrogen nucleus, H11 nucleus, okay, H11 nucleus, then what will be the state of this H11 nucleus? Either the H11 nucleus can orient like this, or H11 nucleus can orient like this. It is already here. See, only two directions are possible. One is this one and one is this one, okay. So each will orient like this. The magnitude of this vector, this angular momentum vector, is 0.86 unit. So both of them have the same magnitude, and its a component in the reference direction will be 0.5. The magnitude will be 0.5. So in order to visualize it in a better way, let me remove the other lines of force which are not in use for our purpose, okay, for understanding purpose. So these two are the orientation of the angular momentum, allowed orientations of the angular momentum for the H11 nucleus. And now we know that the component of this one in the reference direction, this is 0.5, and the component of this one, the reference direction, that is minus 0.5. These are the IZ values. Okay, IZ is equal to 0.5 and IZ is equal to minus 0.5. Okay, these are the two possible IZ values. Now you know that the mu Z and IZ will have the same direction. We already proved that, right? Mu Z and IZ have the same direction. Therefore, mu Z will also have the same direction of the IZ. Means the mu Z will be like this. This will be the mu Z corresponding to I z is equal to 0.5. Okay, I am not very much strict about the magnitude of the mu z here because I am at this moment I am only interested in the direction, that is the mu z corresponding to I z is equal to mu z corresponding to Iz is equal to plus half. Let me draw it. Let me write it large. This is the mu z corresponding to Iz is equal to plus half, okay, and this is the mu z. This is the mu z. This one mu z corresponding to Iz is equal to minus half. Okay, so we have two mu z's. Okay, this one is a mu z and this one is also mu z. Okay, so this is the origin. Okay, yeah, this is the mu z or this is the mu z. And what about these two possibilities for the magnetic dipole moment components? Okay, these magnetic dipole moment components are corresponding to two angular momentum components. And you know that actually, if the magnetic moment component is in the first way, it corresponds to a bar magnet. This corresponds to a bar magnet like this. This corresponds to a bar magnet like this. This can be considered as a bar magnet, and the bar magnet, inside the bar magnet, the direction of the line of force is from bottom to top. See, this is the direction of the magnetic moment, means the direction of the line of force is from bottom to top, If inside the magnet, if the magnetic moment is magnetic lines of force is oriented from bottom to top, it means that the south pole is here and north pole is here, because conventionally we are taking the magnetic lines of force inside the magnet is from south to north. So it means that this magnet is oriented in this way, where south pole is in the bottom and north pole is in the top. Okay. And what about this magnet, the second magnet, or the magnet corresponding to the second possible component of the magnetic moment? And that also corresponds to a magnet, and that magnet is like this, right? That magnet is like this, and in this magnet, the magnetic lines of force is from top to bottom, like this, from top to bottom. And if the magnetic lines of force is from top to bottom, it means that the south pole is in the top and north pole is in the bottom. So this is south pole and this is north pole. Here in this case, this is south pole, this is north pole. So we have two types of orientation for the nuclear magnet. In one way, the component of the magnetic moment of the nuclear magnet in the reference direction is in such a way that a bar magnet is placed in the same direction of the applied field, but the south pole is in the bottom and the north pole is in the top. And in the other case, the bar magnet is placed in the same direction of the applied field, but the south pole is in the top and north pole is in the bottom. These two orientations are possible. So this can be considered as the nucleus in one particular state, and this can be considered as the nucleus in another particular state. അപ്പോൾ H11 ന്യൂക്ലിയസിന് ഈ രണ്ട് സ്റ്റേറ്റ്സ് ആണ് പോസിബിൾ ആയിട്ടുള്ളത്. Either the hydrogen nucleus will be in this state or the hydrogen nucleus will be in this state. Now let us check the first state. In the first state, the south pole of the magnet is near the north pole of the external magnet, and the north pole of the nuclear magnet is near the south pole of the external magnet. That is a pretty good arrangement. Okay, because south pole likes north pole and north pole likes south pole. South pole of the tiny magnet likes the north pole of the big magnet, and north pole of the tiny magnet likes the south pole of the big magnet. Pretty good arrangement. They are happy, right? So the magnet will be always happy to stay in this type of an arrangement. So the magnet is placed in a low energy situation, that is very stable situation. So the first arrangement is a stable situation or low energy situation, and in this case this low energy situation is called alpha spin state. So the first arrangement is alpha spin state. But you look at the second arrangement. The south pole of the tiny magnet or nuclear magnet is near the south pole of the external magnet. That is very bad. In order to sit like that, too much problematic to sit like that, right? Okay, south pole of the tiny bar magnet is near the south pole of the external magnet, and north pole of the tiny bar magnet is near the north pole of the external magnet. South pole doesn't like north pole and north pole doesn't like north pole. It's a high energy situation. It's an unstable situation, right? So the second one is a high energy situation, and this high energy situation is called beta spin state. Okay, beta spin state. So we have two spin states for the hydrogen nucleus. The alpha spin state, which is a low energy situation, and beta spin state, which is a high energy situation. Okay, and in the low energy situation or in the alpha spin state, the nuclear magnet is oriented in the same direction of the applied field. You can look inside the magnet. The direction of the magnetic moment is here. It is from bottom to top, and the lines of force of the external magnet is also from bottom to top. It means that the nuclear magnet is oriented in line with the external field. Okay, it is oriented in the same direction of the external field. But in the other case, you can look at the magnetic lines of force. It is from top to bottom, but the magnetic lines of force of the external magnet is from bottom to top. They are in the opposite direction. Okay, so the beta spin state is not oriented in the same direction of the applied field. It is opposing. Okay, so the alpha spin state and beta spin states are there like this, and the alpha spin state is a low energy situation and beta spin state is a high energy situation. Now we were talking about the energy of the alpha spin state and beta spin state. That was a superficial talk, because we already know that if there is attractive energy, then if the magnets are attracting, then they will be in the low energy situation. If there is repulsion, it will have to sit in a high energy situation. This is what we already know superficially, but we don't have any mathematical treatment so far. We have to treat this mathematically. Okay, so now we are going to estimate the interaction of the tiny nuclear bar magnet with the external magnet. It's raining outside. Maybe there will be a lot of noise. Anyway, I hope you can hear me because I have the mic. I hope it is okay. Okay, so now we are going to estimate the interaction. The interaction of the tiny nuclear bar magnet with the external big magnet. Okay, the interaction. So the interaction of the nucleus or the spinning nucleus or spin with the external magnetic field, that the extent of interaction, that is equal to mu z into Bz, where Bz is the strength of the applied field. We have applied a field here, right? This is the applied field. The strength of the applied field is Bz. It is called Bz because the applied field is in the Z direction. And in certain textbooks you can see that the strength of the applied field is B0. It's totally fine, no problem. But for the moment here we are considering the external field as Bz. Okay, that will be easier for us. So Bz is the strength of the applied field, and mu Z is the component of the magnetic moment in the Z direction. In that case, the interaction is equal to mu Z into Bz. That is the interaction. Or the energy of a particular spin state. The energy of a particular spin state is equal to energy of a particular spin state is equal to mu Z into Bz, or in the case, what is mu Z? G beta n Iz. So we can write G beta n Iz into Bz. So if you want to find the energy difference between these two spin states, okay, you want to find out the energy difference between the two spin states, or you want to find out the energy difference between any successive spin states, okay, then you can find it out easily from here. That is, the energy difference delta E is equal to G beta n Iz into Bz minus, that is the energy of the state with the particular value of Iz, minus energy of the next state with the next possible Iz value. Okay, that is G beta n. What is the next possible Iz value? Okay, you know that Iz values are differing by 1. Two successive Iz values തമ്മിലുള്ള difference നോക്കിക്കഴിഞ്ഞാൽ 1 ആണ് അല്ലേ? നിങ്ങൾ എവിടെ നോക്കിയാലും മതി. നമ്മൾ ആദ്യത്തെ കേസിലാണെന്നുണ്ടെങ്കിൽ Iz is integral spin ആയാലും half integral spin ആയാലും, if Iz is equal to 2, then I is equal to 2, then no, S is equal to 2, then Iz values were 2, 1, 0, minus 1, minus 2. What is the value between two successive Iz values? 1. അല്ലേ? അതുപോലെ if Iz is equal to half, what is the spin is equal to half, then what are the Iz values? Plus half, minus half. What are the difference between two successive Iz values? 1. The difference between half and minus half, that is equal to 1. So the next possible Iz value for the successive state is Iz minus 1, Iz minus 1 into Bz. Okay, so these are the energy of the two successive spin states, and the energy difference, we are taking the modulus of this one because whatever may be the Iz values, the energy difference in positive is taken as the energy difference. Okay, and therefore that is equal to G beta n Iz Bz, G beta n Iz into Bz minus G beta n Iz Bz. Okay, I just expanded this one. Minus, no, that is plus, minus into minus, that is plus G beta n into 1 into Bz. Okay, this one. So these are cancelled, and what is remaining is delta E is equal to G beta n into Bz, G beta n Bz. Okay, that is the energy difference between two successive spin states. So if you want to find out the energy difference between these two spin states, that is equal to G beta n into Bz, where Bz is the strength of the applied field. So it means that there is an energy difference, and corresponding to that energy difference there will be a frequency. Okay, so we can find out the frequency corresponding to the energy difference between these two spin states. The frequency nu is equal to delta E divided by H, because we know that E is equal to H nu, therefore nu is equal to delta E divided by H, that is nu corresponding to the energy difference between the two successive spin states, that is equal to G beta n Bz divided by h. Okay, that is the frequency corresponding to the energy difference. So we can find out what is the frequency corresponding to the energy difference between alpha spin state and beta spin state of the hydrogen nucleus. We can find it out. Okay, let us find it out. What is the frequency corresponding to the energy difference between alpha spin state and beta spin state? So the frequency corresponding to the energy difference is equal to G beta and Bz divided by H. Let us substitute the values for this one. G in the case of hydrogen nucleus is equal to 5.585, okay, into beta n, that is nuclear magneton, its value is 5.05 into 10 raised to minus 27 joules per Tesla into Bz. Bz is the applied field. So I am going to decide which applied field I am giving, right? That depends upon my facility, in which lab I am working, what is the field available there, that is what I am giving. So Bz, in this case what I am applying is Bz is equal to 2.3487 Tesla, 2.3487 Tesla, that is the field I am giving. Okay, so let me give this field 2.3487 Tesla, 87 Tesla divided by H. H is equal to 6.626 into 10 raised to minus 34 joule second. Okay, so that is nu corresponding to the energy difference between alpha spin state and beta spin state. Therefore, that is equal to, you can take your calculator and find it out what is the value. I have already done this. The value is 100 into 10 raised to 6 second inverse, right? Joule and joule are cancelled. Tesla raised to minus 1. Tesla are cancelled. Then what's remaining is a second in the denominator. Therefore, the unit is second inverse, or you can write hertz. Okay, 100 into 10 raised to 6 hertz, or I can write 100 megahertz, because 10 raised to hertz is 1 megahertz, 100 megahertz. So the frequency corresponding to the energy difference between alpha spin state and beta spin state for the hydrogen nucleus when we are applying an external field of 2.3487 Tesla is 100 megahertz. So this frequency actually depends on the applied field. If the applied field is very big, means if the Bz can assume a greater value, then the nu will also can also assume a greater value, or the frequency will be a greater, much greater, and the frequency will be lower if we are applying a lower field or a small field. Okay, so this depends upon the field strength. So when the field is this one, here is the frequency. So there is an energy difference between the alpha spin state and beta spin state. And this energy difference, if you are looking at the electromagnetic spectrum, and this energy difference, that is 100 megahertz in this particular case, that falls in the radio frequency range of the electromagnetic spectrum. Radio frequency range. Radio frequency range. Radio frequency range of the electromagnetic spectrum. What does it mean? So if you are placing the hydrogen nucleus in an external magnetic field, then the hydrogen nucleus will have a magnetic moment associated with that. That magnetic moment will interact with the external magnetic field, so that both spin states for the hydrogen nucleus, okay, will have different energy, and the difference in energy between these two spin states will fall under the radio frequency range of the electromagnetic spectrum. Therefore, if you are giving radio frequency electromagnetic radiation to this hydrogen nucleus, what will happen? Yeah, if there is exact frequency corresponding to the energy difference, then that frequency will be absorbed by the hydrogen nucleus. It will be absorbed by the hydrogen nucleus, and it can make a transition from the alpha spin state to the high energy beta spin state. Okay, that is what is actually going to happen. So, but there are some mechanism behind this absorption of electromagnetic radiation that we will explain in the next class. We have to learn about an important phenomenon of precisional motion or Larmor precession that we will learn in the next class. But what you understood today is that the nuclei will act like tiny bar magnets because of its spin, and these bar magnets will interact with the external magnetic field. Okay, and because of this interaction, there will be the energy difference between the allowed spin states. Okay, and this energy difference will fall under the radio frequency range of the electromagnetic spectrum. So, if you are looking at H12 nucleus, how many spin states will be there? 3 spin states will be there, one corresponding to Iz is equal to +1, another state corresponding Iz is equal to 0, and another one corresponding to Iz is equal to -1. That is the case for H12. There are 3 spin states are possible. Here only 2 spin states are possible. In the case of H11, there are 3 spin states are possible. Corresponding to these 3 spin states, there will be the corresponding magnetic moment also. Those magnetic moment can also interact with the external field, so that there will be 3 energy levels, right? And 3 energy levels. Therefore, there will be there is also possible the transition from a low energy to a high energy. Such transitions are possible, and they will have they will also fall under the radio frequency range of the electromagnetic spectrum. But actually, you can vary this frequency just by varying the applied field. Okay, therefore, frequency always depends upon the applied field. Here, what you have to note is that here I have calculated a frequency nu. Okay, and that frequency I have calculated for the hydrogen nucleus. But you have to remember that here I have calculated the frequency for a bare hydrogen nucleus, means a hydrogen without any electron cloud around it. Okay, bare hydrogen nucleus, or that hydrogen nucleus is completely naked, there is no electron density around it. For such a nucleus only I have calculated this frequency. So, if you are placing a bare hydrogen nucleus, don't ask me how, okay, but hypothetically, if you are placing a bare hydrogen nucleus in an external magnetic field, that bare hydrogen nucleus will have the alpha spin state and beta spin state, and that energy difference between those spin states will be equal to 100 megahertz if the field is 2.3487 Tesla. Okay. So, if we are operating a NMR spectrometer at this magnetic field 2.3487 Tesla for measuring the NMR spectrum of the hydrogen, then we can call this machine as a 100 megahertz machine. So, if you are calling any machine as 100 megahertz machine, it means that when you are placing the bare hydrogen nucleus in the magnet of that machine, then the energy difference between the alpha spin state and beta spin state will be equal to 100 megahertz. Okay, and that is very important. So, this is the meaning of a 100 megahertz machine, 200 megahertz machine, 500 megahertz machine, etc. If it is a 200 megahertz machine, what does it mean? You have to apply a field strength which is double of this one. Okay, 2.3487 Tesla double of the field ആണ് നിങ്ങൾ apply ചെയ്യുന്നുണ്ടെങ്കിൽ നിങ്ങൾക്ക് എന്തായിരിക്കും കിട്ടുന്നത് 200 megahertz ആയിരിക്കും ഇവിടെ കിട്ടുന്നത്. അതിനെയാണ് നമ്മൾ 200 megahertz NMR machine എന്ന് വിളിക്കുന്നത്. 1000 megahertz machine. Some well-equipped laboratories has this machine also, 1000 megahertz machine also. So, all this depends upon the magnetic field strength. ആ മെഷീനകത്തുള്ള മാഗ്നറ്റിൻ്റെ ഫീൽഡിൻ്റെ സ്ട്രെങ്തിനെ ഡിപ്പെൻഡ് ചെയ്തിരിക്കും നമ്മൾ വിളിക്കുന്ന ഈ 100 മെഗാഹെർട്സ്, 200 മെഗാഹെർട്സ്, 300 മെഗാഹെർട്സ് എന്നൊക്കെ പറയുന്നത്. ഓക്കെ, അപ്പം നിങ്ങൾ if you are going for doing your project after this MSc and you are seeing a 100 megahertz NMR machine, you will see a machine, Bruker machine or something like that, whatever it may be. Then if it is if somebody says that this is a 100 megahertz machine or this is a 500 megahertz machine, you have to understand what does it mean. Okay, it means that for the hydrogen nucleus, the energy difference between the alpha spin state and beta spin state will be equal to 100 megahertz or 200 megahertz or 500 megahertz, whatever it may be. Okay, if the hydrogen nucleus is a bare hydrogen nucleus, that's the meaning. Okay, I hope you understood this many things, and today we discussed on the interaction of the nuclear spin with the external magnet. Hope you enjoyed this lecture. Then we will see again with another topic in the next class. Bye.